All right, in the last section we covered, we did some work with derivatives of exponential functions. And I just want to review those two derivatives here. So I'm going to jot them down on the board. Okay. In terms of exponential functions, we had, first of all, what if we have e to the x and we want to take the derivative of that? So we want to take the derivative of e to some power. Well, we decided that the derivative of e to the x is e to the x. And then if this becomes a more complicated function that has its own derivative, we talked about how the chain rule can work in that situation. Okay? But this is the first definition I want to remind us of. And the second definition is, what if we don't have an e down here? What if we have some other number, like 2 to the x, or 7 to the x, or some other value? What if it's a to the x? You know, some number a raised to the x power. Well, we decided that it's a lot like this one in the fact that a to the x is still part of the derivative, but now we need to multiply by a constant. We have to multiply by the natural log of a. So if it's 2 to the x, the derivative is 2 to the x times the natural log of 2. Okay? And so these were our two definitions for derivatives of exponential functions. Okay? Now, today we want to look at the inverse of exponential functions. We want to look at what are called logarithm functions or logarithmic functions. What are the derivatives of those two? And we'll come up with two definitions similar to these two right here. Okay? So what if we look at logarithm functions? The two derivatives that we are interested in, one of them today we'll look at is the derivative of the natural logarithm, which is the inverse of e to the x. And then we will also look at the derivative of, what if we just have a logarithm base a of x, which is the inverse of just a to the x. Okay, so these will be the two answers or the two definitions that we are looking for today. Now, we'll start with the natural logarithm of x because it's actually the easier one of the two. Okay? And the way we will do this, let's start out with our definition. The same definition we've been using this whole semester. Okay? Where we take the function evaluated at some point just a little bit to the right of where we're interested in, minus the function at x, all divided by h. And then we take the limit as h approaches 0. Okay? Now let's set this up for the function f of x equals the natural log of x. Let's just set it up and see how it works here. Okay, so what would be my function evaluated at x plus h? Well, instead of just ln of x, it would be the ln of what? X plus h. Yes, I'm just evaluating this natural logarithm function at some point just a little bit to the right of where I'm interested in. Okay, then minus the original function, ln of x, and then all divided by h. Now, what I want to do is I want to use this definition. This basically is a slope. Okay? I want to use this slope to start making a table of values. Okay? And on our table of values, we're going to have values of x, and we're going to have values for the derivative of the natural log. Okay? Now, remember, we want h to be really close to 0. So when we start plugging this in your calculator, you pick a very small number for h, and I don't care what you choose. If you choose 0.01, if you choose 0.000001, just pick a really small number for h. That goes in here. The x value that you will sub in will be the number that's along this side right here. Okay? And what I want you to do then is go ahead and do this calculation for various values of x, and let's see what these values are for the slope. Let's see what the derivative values are. And I want to start with x equals 1. Okay? So in your calculators, and I'll demonstrate up here on mine as well, let's plug in 1 for x, and let's plug in a really small value for h and see what we come up with. Okay? So we've got the natural logarithm of 1 plus a really small h minus the natural logarithm of 1. I'm going to go ahead and push equals. And then I want to divide by that really small h. And my answer, 0.9995, we'll assume that that is really, really close to 1. Okay? All right. Now, we continue on here. Let's pick a different value for x. Let's pick 2 for x. And then let's pick 3 for x. And we'll go all the way down to 4. And maybe by the time we get to 4, we should hopefully notice a pattern. This is actually a very nice derivative here. Okay? So let me go ahead and plug in some more of these values. Some of you plug in 2, some of you do 3, some of you do 4. Let's kind of spread it out here. And let's see what these values are. Tell me what you get when you sub in these next 3 values of x. .5 for 2. Okay? What about if we try 3 or 4? 4 is 0.25, and 3 is 0.33. Okay. Now, just looking at this table, the first thing that we notice on the derivatives is that they are getting less. Okay, here's a derivative of 1, here's 0.5, 0.3, 0.2. They're getting less, but they are all still positive, aren't they? Okay, so we notice a couple of things. But the key idea, though, is there a nice pattern that's developing? You know, if we convert these over to fractions, yeah, what are these fractions here? Well, this is 1/2, this is 1/3, and this is 1/4. And so we see a nice relation between the left side and the right side of the table. What if I just leave this as an x? What if I pick any number? What does it appear the derivative is? Just 1 over that number, exactly. And that is the definition for this derivative back over here. The derivative for the natural log of x is 1 over x. Okay? So that's a nice little pattern that develops here. So this becomes, a very nice derivative. It changes from a logarithm function over to just a 1 over x, just a nice little rational function. Okay? So that's one of our derivatives that we will use here today. Okay. The second derivative, I'm going to approach it a little differently, this log base a of x. I don't want to approach it from the definition this time. Let's just try it a different way. Okay. So let's start out with the definition, or let's just start out with the equation. F of x equals log base a of x. And again, I'm going to go do a little bit of theory with you this time. This is not anything you'll have to ever reproduce, but sometimes it's good to just see the mathematics behind where this is coming from here. Okay? All right, what we're going to do is we want to rewrite this as an exponential function. And the reason we want to change it over is because then I can use these previous definitions I already know. Okay? So my question would be, and let's see if anybody remembers how to do this, how do we rewrite this logarithm function as an exponential function? I'm going to have something at the base, I'm going to have an exponent, and then I'm going to have an answer. Do you remember what goes where? Okay. The a is the base, so the a goes right here in this location. Okay. Now I've got an x and I've got an f of x. Which one should be up here? It's the x. It's the f of x. A to the f of x equals x. That's how we switch from exponential to logarithm form, but if you haven't done it for a while, it's pretty easy to forget that. Okay? So here's our definition, a to the f of x equals x. And all I did was rewrite this in a different form. Okay? Kind of like we can do with fractions. We can sometimes rewrite them in a little different variation. Okay? Now what I want to do is I want to come back over and use this definition of exponential derivatives. Since the left side is equal to the right side, if I was to take the derivative of both sides, those should also be equal to each other. So that's what we will do. We want to take the derivative of the left side and the derivative of the right side. Well, let's do the easy one first. What's the derivative of the right side? What's the derivative of x? 1. Okay, so that was the easy one. Now, the one that's a little more difficult. What if I wanted to take the derivative of a to some power f of x? Okay. What's the derivative of a to the f of x? Well, first it's a to the f of x times the ln of a, isn't it? Okay, that's the first part of the derivative. So a to the f of x times the ln of a. But now, over here, x is literally just x. Here we have a function f of x. So what do we have to multiply by? Well, we have to multiply, according to the chain rule, we have to multiply by the derivative of this up here, whatever it comes out to be. Okay? So for example, I'm going to step off to the side here for just a second. What if I gave you the equation 7 to the x squared? And we've done this derivatives like this before, and I said, what's the derivative of 7 to the x squared? Well, the first thing we would say is, well, it's still 7 to the x squared, We would multiply by the ln of 7. Okay? But since x squared has a derivative, we then need to use the chain rule and multiply by its derivative. And what's the derivative of x squared? Well, it would be 2x. That's exactly what I'm doing over here, except we just don't know what this function is. So we just have to write f prime of x for right now, because we don't know what that derivative is. Okay? All right, now back over to here, the thing that we're really interested in is we're interested in solving for the derivative, because that's what we want to figure out. What's the derivative of this function? Okay? So if I have all of this times f of x, how could I solve this algebraically for f of x? What would I do with this first part here? Okay, if I've got multiplication here, the way that I move this over to the other side is I divide it over. Right, okay? So my answer for this, if I just take and divide all this over, I'll have 1 over a to the f of x ln of a. Just did a big division is what I did here. Now, I'm going to make one more substitution here. A to the f of x is the same thing as what from up above here? A to the f of x, that's the same thing as x, isn't it? And that would be a lot easier if we just replace this with an x. And so let's go ahead and do that. So 1 over x ln of a. This is our answer. This is our derivative for logarithm base a of x. Okay, let me write it down, and then I want to talk about it. This is just a combination of two derivatives almost. Okay? First of all, we notice that this is a logarithm function, and this is a logarithm function, and don't they both have a 1 over x component in their derivative? Of course, yes. Okay? What else do we have happening over here? All right, well, let's come back to this example over here. Excuse me. Come back over here to this exponential example. Okay? In the exponential example, we had to multiply by the ln of a as part of our derivative. Well, what do we do on the inverse function? Instead of multiplying, we divide by ln of a, don't we? Okay, and so again, there's a couple of things. If we put this definition and this definition together, it makes some sense why we have 1 over x times ln of a here. Okay, so these are the two definitions that we will use today. Now let's go ahead and get to some specific examples. Okay. Get to the right page here, and I'll find some examples to go through. All right, what if we start out with this equation? Y equals the natural log of negative 4x. And we want to determine the derivative, so we want dy dx. Now, your questions on homework will not have just ln of x's in them very often. We will more than likely have some type of chain rule involved. Okay? All right, but what does the definition say that we need to begin with? What's the derivative of the natural log of something? 1 over the something, right? So the first part of my derivative here will be 1 over negative 4x. 1 over the stuff in parentheses. Okay? Now, the question then becomes, do I have a chain rule in here? Is there a derivative inside the parentheses? And the answer is yes. What is it? Negative 4. Right, the derivative of negative 4x is negative 4. So I need to multiply by the derivative of inside the parentheses, which is negative 4. Okay, that's the only difference. That's how the chain rule gets involved in these logarithm functions. Now, can this be simplified? The answer is yes. This negative 4 is really up here in the numerator. This negative 4 is really in the denominator, so they cancel off. And so this one actually simplifies all the way down to 1 over x, although that is somewhat coincidental that it matches up here. You know, don't assume that everything is going to simplify down to 1 over x, because they won't. Okay, this one just did. All right, another example. What if I have y equals the natural log of 2x squared minus 7x? And we are interested in the derivative of this function. All right, what does the natural logarithm tell us to do? The derivative is 1 over whatever's in parentheses, exactly. So that's the first part. 1 over 2x squared minus 7x. Okay. But then I look inside the parenthesis, and is there a derivative in there? Yes. What is it? 4x minus 7. Okay. And so the answer is 1 over whatever's in parentheses times the derivative inside the parentheses. A lot of times you will see this simplified in this way. The denominator will still be whatever was in parentheses, but they will, instead of writing this chain rule out here in the front, because it's always multiplied by this 1, okay, usually they'll write the derivative inside the parentheses up on top, okay, and just turn it into a simple fraction this way. Okay, so these are both equivalent. It doesn't matter which form that you write it in, as far as I'm concerned. All right, what if we have this example? The natural log of the square root of 2x plus 1. Again, we're interested in the derivative, so where do I start? Yep, exactly. Okay, as soon as I see there's a natural logarithm out here, I realize part of the derivative is just 1 over, in this case, what's underneath the square root. Okay, 1 over the square root of 2x plus 1. Okay, now it's almost like I'm done with the natural log part of the derivative, so I can kind of hide that, and now I need to say, well, what's the derivative of what's left? And how do we take the derivative of the square root of something? Think about it as to the 1/2, and so what would the derivative be here? Okay, I'm going to go in this order. 1/2 times 2x plus 1 to the what? To the negative 1/2, right. Okay? So now it's almost like I've done the natural log part of the derivative, I've done the square root part of the derivative, and now I look inside the square root, and is there a derivative in there? Yes, and what is it? It's a 2. So I have to multiply by 2. So this is almost like 2 links in the chain on a chain rule. You know, we had to take a derivative for the outside function, but then we had to look inside for another derivative, and then we had to look inside the parentheses there for another derivative. So this one actually had 3 steps to it. Okay? And this is where it gets confusing. When you get a whole bunch of functions here, that's where derivatives become difficult. But try to think about it one at a time. I did the logarithm first, then I did the square root, and then I went inside the square root for the just linear function. Okay? In terms of simplifying this, I don't know if there's much that we want to that's necessary to do, but if you're looking in the back of the book on an odd-numbered question, you want to see if your answer matches up, my guess is they will definitely simplify those two. 1/2 times 2 is 1, so you won't see either one of those components. Okay? And then the other thing is, on this example, they probably would do quite a bit of simplifying because 2x plus 1, and here's another 2x plus 1. So those can actually be joined together. So let's talk about how we would algebraically join those together. First of all, if this is in the negative 1/2 power, what if I move it to the denominator? Positive 1/2 power, right. So if I got a positive 1/2 power in the denominator, this is to the positive 1/2 power. So what if I put those together? A 1/2 power and then another 1/2 power would be, okay, careful here. If I have, and I'll, again, off to the side, what if I have 1 over x squared times x cubed? Would be to the 5th or to the 6th? Should be to the 5th, right. We want to add those exponents together. So if I have a 1/2 power and a 1/2 power, that is a first power, right, okay? So they would actually simplify this thing all the way down to 1 over 2x plus 1, and if you're not comfortable with the algebra, you've got this. This is correct, but this looks a lot different than 1 over 2x plus 1, okay? So that's why we have to stress the algebra a little bit. If you want to double check your answers, there's a lot of algebra going on to get down to just 1 over 2x plus 1. Okay? But that's the answer for number 8. Let's see. What if we do this one next? Y equals negative 3x times the natural log of x plus 2. Now, the first thing that I hope you notice, what makes this problem a little different than some of the other ones? What do we have to use on this one that we haven't had to use before? Product rule, right. Okay? Because I have a function with an x out here in the front, and then I have another function with an x right here. So this needs to be separated and thought about as a product rule. Okay? All right, so let's work through this product rule and see what we come up with. All right, the first part of the product rule says just take one of the parts and rewrite them as it is, and then I multiply by the derivative of the other piece. And what's the derivative of ln of x plus 2? Okay, 1 over x plus 2. Then I look inside the parenthesis, and what's the derivative in here? Just a 1. So, I mean, there really was a chain rule, but it was just times 1. All right, so that's the first times the derivative of the second. Now I need to add on the second times the derivative of the first. So I rewrite the second part. What's the derivative of the first part? Negative 3. Now again, in terms of simplifying, we probably won't be able to do a whole lot with this one. Probably all they would do on this first part is rewrite it as just one fraction. Okay. And on the second part, the only thing they might do is write that constant number out in front as opposed to at the end. But otherwise, I mean, there's really not a lot that happened on this one. Okay? So this would be our derivative for that product rule. Okay, very good. Let's see, what if we do a quotient rule example? What if we've got g of x equals the ln of x divided by 4x plus 7? Okay. All right, what's the quotient rule say again? Okay. And again, I don't know which way I remember telling you this, but we start with the bottom times the derivative of the top. Okay, whether you take the derivative first or you rewrite the bottom first, it doesn't matter. Okay, so I've got the bottom component times the derivative of the top, which happens to be what? 1 over x. Okay, then minus the top component times the derivative from the bottom. Times 4. And then divided by the bottom component squared. All right. Again, in terms of simplifying on this one, I don't know how much we'll be able to do. Okay. Definitely we want to leave the bottom as it is. There's really, I can't think of any good reason why we would ever want to multiply out that squared on the bottom. So never usually want to do anything with it. Okay. The only thing that could possibly be done up here, although it doesn't really help a whole lot, is we could do a distributive property and run it through here. The big advantage would be if anything, when we did that, if anything ever canceled off with over here, but it's not going to happen. So again, I don't think there's a whole lot of benefit to actually running this distributive through. We'll probably just go ahead and leave it the way it is. Minus 4 ln of x, and that's probably good enough. Okay. All right, so there's an example of the quotient rule with it. Next example I want to look at, we've done a whole bunch of work with natural logarithm derivatives. Now what if we go back and look at this other definition, the regular logarithm? Let's do a couple of examples with it. Let's take logarithm of 2x minus 3. So again, we notice difference on this example, we just don't have 1 over x. We've got a little bit of an extra component we don't want to forget. All right, so dy dx, what is the derivative of this function? Well, first of all, I still have a what as my derivative? I still have a 1 over whatever's in parentheses, don't I? So I still have 1 over 2x minus 3. That's still part of my derivative. However, I need to multiply by what here? Okay. Now, the problem is here we have an a, and here we don't see anything. And so if we don't see anything, what's understood to be here? There's a 10, right. If we don't have anything here, that is understood to be a 10. You know, just like when you're taking a square root, you usually don't write a 2 out here. It's just understood that it's there. Same thing with a logarithm. If you don't see anything, there's really a 10. So I need to multiply this denominator by what? ln of 10, exactly. Okay. That's the only difference between a natural logarithm's derivative and a logarithm derivative, is that we just have to multiply by something extra on the bottom. Okay. Now, I've taken the logarithm part of the derivative. Is there a chain rule piece here? Is there a derivative inside the parentheses? Yes, what is it? Yeah, just simply a 2. Okay? And so my guess is if this was being simplified, they would probably write it this way. Okay? Usually in mathematics, we take numbers. ln of 10 is just a number. You could punch it in your calculator and get the decimal for it. Usually they'll write the number in front of the variable term. Okay? So that'd be the only reason I'd say they'd probably write it this way. Okay? So there's an example with a logarithm derivative. Let's just do one more with a logarithm. Logarithm base 7 square root 3x plus 5. All right, where do I start taking this derivative? Okay, exactly. 1 over whatever's in parentheses. Or in this case, underneath the square root, sure. 1 over square root 3x plus 5. Okay, what else needs to happen here? ln of 7. I have to multiply by that constant on the denominator, sure. All right, so that takes care of the logarithm part of this derivative. So I can ignore log base 7 now. Now I look at what's left and I decide, is there a derivative from it? Yes, what is it? 1/2 3x plus 5 to the negative 1/2. Okay, so now it's almost like I've done the square root. So now I look and see, is there a derivative from underneath the square root? Yes, and it is a 3. So I would have to multiply by 3. So again, this was another example where we had multiple links in the chain rule. Okay? We took the logarithm derivative, then the square root derivative, and then the derivative of just the linear function. So we had 3 functions here all embedded together. Okay? All right, questions with logarithm derivatives. These are the 2 definitions you have to know. And if you can follow them and then use the chain rule is the biggest thing. If you can use the chain rule appropriately, you'll probably do fine with these derivatives. Okay. All right. Switching gears into another concept here. I've hinted at this concept for, the last 2 or 3 weeks now. And so, but today we finally formally talk about what it means for a function to be increasing, decreasing, and then as well as finding locations of maximums and minimums on graphs. Okay? And so that's this next concept here, is we're going to look at increasing and decreasing functions. And then here in a little bit we'll talk about maximum and minimums on graphs. Now, I think it would be very easy. All of you could ace this if it was a quiz question. If I just gave you a graph and told you, just show me where the graph is increasing and where it's decreasing. Everybody intuitively knows what it means for a graph to be increasing or decreasing. Okay? Of course, it just means here the graph is increasing because it is going up. We can see the y values are getting bigger. Now, I want to put down some formal definitions, though, because this is where we'll actually be able to use the calculus to find these values. Okay? If a graph is increasing, one way that we can define that is that we can say, if we pick out 2 x values, x1 and x2, okay, and I'm going to, the book uses x1 and x2. Let me change this to xl and xr, standing for the x value on the left and the x value on the right. Maybe that'll be a little easier to understand here. Okay? So if I pick an x value on the left, smaller than one that's on the right. So I pick here x is 2 and here x is 3, for example. Okay? A graph is increasing. If this is true, then the function on the left-hand side, the y value, has to be smaller than the y value on the right side. This is the formal definition of increasing. Okay? It says that if I pick 2 x values, and let me come over here to the diagram and show you. Okay, here will be my x value on the left. Here will be my x value on the right. Okay? So if I pick an x value on the left and one on the right, if the y-coordinate for the left value is smaller than the y-coordinate for the right value, then the graph has to be going up, doesn't it? If this y value is smaller than this one, it had to be going up. Okay, so that's one way to define increasing. A little confusing though. Okay, but the thing with it is that we're only using x and y coordinates. Okay? How we want to define increasing today in terms of calculus is we want to do this in terms of a derivative. What is true about the derivative of this graph wherever it is increasing? What's true about the derivative or the slope of this graph? Well, here maybe the slope is 5, here it's 4, here it's 3, but they're all what type of values? Positive values, good. Okay. So another way to define this is the confusing way. The easier way with calculus to define increasing is if the first derivative is bigger than 0. Then we know the graph must be increasing because we have a positive slope. Okay? And so this is how we want to look at problems today. If we have a question that says, find out where a function is increasing, we're going to take the first derivative and we're going to find out where that first derivative is bigger than 0. Okay? All right. Similarly, we can define decreasing, and I'll put the complicated definition and then the easier one. Okay? If we have two values, again, a left and a right value for x's, okay, then what needs to be true if the graph is decreasing? So if I pick one x value and then another x value over here, what needs to be true about their y values? Well, this y value has to be bigger than this y value, doesn't it? So this is saying then the y value on the left, has to be bigger than the y value on the right. That's how we know that a graph is decreasing. Okay? So it's almost the same except we just switch the sign on the second part. Okay? Easier way to do this with calculus, how do we know when a function is decreasing? If the first derivative is what? Less than 0. Sure. If the slope of the graph is negative, that means we have to be decreasing. Okay? Now, the big question that comes up though, okay, how do we get on graphs, how do we change from a graph going increasing and then changes over to decreasing or vice versa? What type of things on a graph make it change from increasing to decreasing? Okay? One of them is pretty obvious on my drawing here. What's one way that I can change from being increasing to decreasing? What happens up here? What's true about the slope up here? If I ever get a slope of 0, that is a possible place where I could change from increasing to decreasing. Okay? So if we come over here, changing from increasing to decreasing or vice versa. Okay? One of the ways this can happen is if we ever see a derivative that's equal to 0. That is a possible location. Now, it doesn't always happen this way though. Okay? An example, I'll just draw it and erase it here. Okay? An example of a place where we would have a slope of 0 but it wouldn't change might be the graph of y equals x cubed. Okay? We've got this S type of shape. Here we've got positive slopes, but then it levels off, and right here at 0 we actually get a slope of 0. But did the graph was increasing, but then when it got to 0, did it change over to decreasing? No, it actually continued to increase. So it's not always going to make it change from increasing to decreasing, but there's a good chance that it will. Okay, so we want to look at any places where the derivative is 0. That's going to be a key place for us. Okay. The second time, or the second way that we can change from increasing to decreasing, this is a little bit harder one. I don't have it drawn up here on this example. Okay? But the second way that this can happen is if we ever have a discontinuity in the graph. Discontinuity, I think I spelled that right. Okay? And here's what I mean. What if we have a vertical asymptote in our graph? Okay? So my graph is increasing for a while, but then I have a vertical asymptote here somewhere, and then on the other side the graph does this. So it was increasing for a while, and then it hit that asymptote, and now it's starting to decrease. So that's the second place where we can get a change from increasing to decreasing is if there's ever any discontinuities. And it doesn't have to be just a vertical asymptote. We talked about holes in graphs. We talked about jumps on graphs. Any type of discontinuity could be a possible change from increasing to decreasing. Okay? Now, the names that we give these numbers, wherever the derivative is 0 and wherever we have a discontinuity in a graph, these are both called critical numbers. And so the first step for us when we're trying to determine where a graph is increasing and decreasing, the first step is to find where all the critical numbers are at. Then once we find the critical numbers, then we can determine where it's increasing and where it's decreasing. Okay, so this will be our approach here today. Step 1 is find the critical numbers. Step 2 is then go ahead and pick where it's increasing and decreasing. Okay. I want to get into a specific example here. This will make more sense if we look at an actual example, an actual problem here. Okay. Let's just take a polynomial as our first example. Start out with an easy one here. 2/3 times x cubed minus x squared minus 24x minus 4. And our question or our goal is, where's this graph increasing and where's this graph decreasing? And we want to use calculus to find out these values. Now, this is an easy enough example. You could plot it on your calculator and you can very quickly tell where it's increasing and where it's decreasing and so forth. Okay? But as we progress into more difficult examples, it will not be as easy just to see them on the calculator. And that's why we have this calculus to help us find out where these values are at. Okay? All right, step 1 is to find all the critical numbers. And the critical numbers occur wherever we have derivative equal to 0 and wherever we have discontinuities. I like to start with discontinuities first. Okay. As we look at this graph, do polynomials have discontinuities? Do polynomials have holes in the graph? No, because we don't have any division on them. Do they have any vertical asymptotes? No, because we don't have any division on them. Okay? There's no discontinuities in polynomials because there's no division involved. And that's whenever we divide, that's when we get our problem areas. Okay? So we don't have to worry about any discontinuities. The only thing we have to look for, where's the derivative equal to 0? So let's go ahead and find it. What is f prime of x for this given polynomial? Well, if I bring the 3 down, what's 3 times 2/3? 2. And then I decrease the power by 1, so 2x squared. Okay, what's the next component? Sure, minus 2x here. Minus 24, and the derivative of negative 4, 0. Right, so I just take the first derivative. Now, I want to set that first derivative equal to 0. And here's where the factoring is going to start coming into play. We did factoring the first day of class. Now you're really going to start to see it a lot. Whenever we set functions equal to 0, if we can factor, that is to our advantage. Okay? All right, first thing I notice, what can be factored out of here? I can factor out a 2. X squared minus x minus 12. Now I need to look at what's left over here. Can I factor this into 2 different binomials? More than likely, the answer is going to be yes. The book is going to choose nice numbers that will factor easily. Okay? Will you see what the factors are? Okay? Yep, 3 and negative 4. X plus 3 and x minus 4. Those are the factors. Okay? All right. Now, our goal is then to figure out where does this polynomial turn into 0? What are the values of x that can zero this thing out? 4 and negative 3 are the only 2 numbers that will zero this out, right? Okay. Be careful, definitely 2 does not zero this out, because if we subbed in 2 and wherever we see an x, that would not turn into 0. Okay, so these are my 2 critical numbers right here, 4 and negative 3. Now, to finish off this problem, here's what we do. We're going to imagine a number line of all possible values from negative infinity to infinity. Okay? The only places that I have to worry about something changing are at these numbers. So my first interval is going to start at negative infinity, and it's going to continue until I get to negative 3, wherever negative 3 is at. I don't know if it's increasing or if it's decreasing in here, but does it ever change from one to the other? No. The only place it can change is at a critical number. So I know that either this graph is completely increasing the whole time in here, or it is completely decreasing the whole time. Okay, we'll find out in a minute which one it is. Okay? Now, the next interval that I will look at, well, I go from -3 to the next critical number. Okay? And in this case, +4 is the next critical number. So between -3 and 4, the graph will either be increasing the whole time or else it will be decreasing the whole time. Okay? And then my last interval would be from where to where? From 4 on to infinity, right? Because I've run out of critical numbers, and so it will have to do the same thing from 4 on the rest of the problem. Okay? So this is how we use critical numbers. We split up our number line at those critical numbers, and we know that nothing can change in each one of these intervals. Now, the last question that comes up then is, well, is it increasing in here or is it decreasing? Now, again, this is an easy enough example. You could just plot this function on your calculator and you could tell right away if this is increasing or decreasing. Okay? When we get to more difficult examples, and it's a little bit hard to tell, where the line looks like it's almost going straight across, okay, how do we know if it's increasing or decreasing? Well, the easiest way to do this is to pick a number inside this interval. Any number between -infinity and -3. Okay? What do we want to choose? Well, usually we try to pick a nice number calculation-wise. So let's pick -5. Okay, so I'm going to choose a number inside this interval. I'm going to take that number and just in my mind, I'm going to sub it into this derivative. Okay, now, the only thing we really care about here, we don't care about the actual number. The only thing we care about is this number positive or is it negative? Because what would it mean if I subbed a number into the derivative and it came out positive? It has to be increasing, doesn't it? If I sub in a number into the derivative and it's positive, that means the graph's going up. If I sub in a number to the derivative and it's negative, then the graph is going down, decreasing. Okay? So let's do this real quick. Let me show you how I would do this in my mind here. Okay. Usually the factored form is the easiest one to work with. So let's just take this factored form. If I sub in -5, -5 minus 4, what type of number is that? It's a negative number, right? And that's all I need to know. It's just a negative number. -5 plus 3. That's also a negative number. What's a negative number times another negative number times 2? It's positive, isn't it? So I know that my derivative is positive, which means what has to be happening in here? It has to be increasing the whole time. It's increasing at -5, and because there's no other critical numbers, it can never change to decreasing anywhere in this interval. Okay? All right. Now I come into the next interval and I choose a number. Okay? Probably what's the nicest number in here? 0 would be a good choice, right? If you can ever pick 0, that's the easiest one to work with. If I sub in 0 here, what type of number? Negative. Here is positive. So what's a negative times a positive times 2? Negative. So what's happening in here? Decreasing. And then I do the same thing in this last interval from 4 to infinity. I pick a number. Maybe 10 is my number. It doesn't matter. If I pick 10 in here, this is a positive. Positive times 2 is definitely positive, so it's increasing. Exactly. Okay? And like I said, it doesn't matter. Don't literally plug in 10 and plug it into your calculator and find the answer. I don't care if this is a +1 or a +100. It doesn't matter. It just means that it's increasing either way. So that's really the only thing that's important. Okay. All right, we'll do some more examples with increasing and decreasing next time, as well as talk about some maximum minimum points.